This is LIGO, which stands for Laser Interferometer Gravitational Wave Observatory. LIGO is comprised of two detectors, one located in Hanford, Washington, and the other in Livingston, Louisiana. However, other laser interferometers exist with the purpose of detecting gravitational waves, like Virgo in Italy, GEO in Germany, and TAMA in Japan. Gravitational waves are ripples in the fabric of spacetime itself that occur when two extremely massive objects like black holes or neutron stars interact with each other in a binary. This description of gravitational waves comes from Albert Einstein's theory of general relativity and remained only a theory until 2015, when LIGO observed the merger of two stellar mass black holes 1.2 billion light-years away, one with a mass 29 times that of the Sun and the other 36 times larger, directly proving their existence. According to the equation E equals mc squared, as the black holes spin closer and closer together and their rotational energy is increased, some mass must be converted into energy. This mass propagates out from the two in the form of gravitational waves. While the scientists at LIGO were able to prove this extraordinary merger, they were only able to deduce from the recorded data that the now merged black hole existed somewhere in a distant galaxy in the region of the southern sky. The reason LIGO could prove this event happened without knowing its exact position in the sky comes down to the nature of LIGO's design and how it's intended to operate. What follows is a simplified explanation of how LIGO detects gravitational waves. When a gravitational wave passes through the Earth, it stretches and squeezes spacetime itself. By the time these waves have traveled 1.2 billion light-years, they are incredibly weak relative to the size of the Earth, but the stretching and squeezing of each of LIGO's 4-kilometer-long arms is just enough to detect their presence. The presence of at least two detectors is required to sort out background gravitational noise that may be polluting the data at one of the detectors. If a semi-truck passes by the detector in Louisiana, it will also produce gravitational waves like any massive object. If the same data isn't recorded in Washington, the data corresponding to the truck driving by can be ruled out. LIGO proved the existence of gravitational waves by firing a single laser beam that is split at the intersection of the device. Half of the beam is sent into each arm, where they travel to a mirror suspended on a pendulum at the end of the arm, before bouncing back toward the intersection. When both halves of the beam rejoin at the intersection, under normal circumstances they should destructively interfere or cancel each other out, and there will be no light observed by the detector. However, when two black holes merge in a distant galaxy sending gravitational waves through spacetime like they did in 2015, one arm is slightly stretched while the other compresses at a length of about 1/1000th the diameter of a proton. When the two beams of light met at the intersection, they had no longer traveled the same distance, so they were unable to fully cancel each other out, and some light is observed at the detector. Encoded in this data of patterns of light is all the information we know about this distant merger, although we know it definitively. Gravitational waves behave just like waves in the ocean, waves of light, or waves of sound. Like a sound wave, the interference pattern observed at LIGO can be shown as a wave pattern. Here you can see the steady yet accelerating in-spiral of the two black holes leading up to their merger, and here is the point at which the black holes merged. This area all the way on the right is the ring down, the time in which the newly formed black hole settles back down into a spherical shape. Gravitational wave detection has the potential to fundamentally change astronomy, giving us the ability to observe faraway events using gravitational waves which are neither absorbed nor reflected by anything that might be in the way of a traditional telescope. This type of detection also gives us the ability to observe phenomena that don't produce any light on the electromagnetic spectrum and therefore cannot be detected by traditional telescopes, such as the interactions and presence of black holes.